Hey everybody, welcome back. This is a bonus video for the chi-square goodness of fit in Excel. As a bonus video, you don't have to watch this, but I just wanted to at least offer you another example showing a walkthrough of calculating the chi-square goodness of fit in Excel before you get into the classroom and have to do these on your own. So let's go ahead and get started. This particular example, we have a machine, it's on a production line, it produces things of different levels of quality. Those levels of quality are Excel, good, and unacceptable. I'm sorry, excellent, good, and unacceptable. I have them listed in column A, rows 3 through 5, and then I have a total in row 6. And this machine has recently had some work done on it, and what we want to figure out is, after the work has been done on this machine, are the things that are being output on this machine of the same level of quality as it was before it had the repairs done. So what we're trying to find out, we would say, is a null hypothesis would state that there are no differences from the frequencies being produced out of this machine at the given quality levels from what it was doing before it had the repairs. Our machine is essentially doing the same level of quality as it was before. No difference. An alternative hypothesis would say that there is a difference from this machine's outputs right now as we see it across the distribution of qualities from our previous understanding and knowledge of this machine, from its historical levels. And so the chi-square is not going to tell us if which particular percentage group is different from the rest. It's not going to tell us if it's doing better or worse than it was before. It's simply going to say that it is different from our previous knowledge, our historical record of this machine's outputs. So what I have here is a sample of 200 items that came off of this machine's line. Of those, 157 are of excellent quality, 42 are of good quality, and 1 is of unacceptable quality. And I'm going to compare this to our previous knowledge that 80% of the items that came off of this machine were of excellent quality, 17% were of good quality, and 3% were of unacceptable quality. And as an Excel sheet here, just for the purpose of the walkthrough, I have some information sort of pre-populated, such as the steps for the chi-square, and some helper cells down below. So let's go ahead and start with some of the helper cells. And the first one is N. N is the total sample size. Now in this case, I already have a total row of 200 underneath there, but if you didn't, for the purposes of the walkthrough, we're going to go ahead and calculate it. Now I could just look at the N, or I could sum it in my head, or if I want to do it a little bit more efficiently and accurately, perhaps with using an Excel function, I'm going to do equal sign sum, and then I'm going to click and drag down the rows of the 3 groups. If you're doing this, make sure you don't include that total of 200 because you'll be counting your total twice. And it says N is 200, and we're good with that. Groups, that is represented by the letter of K. That's how many different quality groups do we have. I can see there, excellent, good, and unacceptable. I could type a 3, or if I want to just improve some of my Excel skills, I'll use a function. So I'm going to use equal sign, count A, count A counts items in the area that you're specifying, but it also allows you to count things that are string text as well as numerical values, where count only looks at the numbers. So in this case, I'm just going to click and drag over my groups, and it tells me that I have 3. Equal proportion. In our previous video, we looked at the students who were being called on in class. There were 5 students that could have been called upon equally. This is not the case. In this case, we are told that there are 3 different quality levels, and they are producing at different percentages of quality. So in this case, no, we do not have equal proportion. Yates continuity correction, Yates CC. This is a special treatment on the math we need to do of the chi-square when we have 1 degree of freedom. So let's go ahead and figure out if we have 1 degree of freedom. Jumping down a couple rows, I am in cell B19, where we're going to calculate the degrees of freedom. So degrees of freedom for a goodness of fit is K minus 1. So I'm going to go ahead and click equal sign, click on my group's K, which is 3, minus 1, and it should tell me 2. It does. And then just for sake of completeness, I'm going to go ahead and list my alpha level. When your N is under 100, an alpha level of 0.01 is fine, 10%. But when we're over 100, less than 1,000, I usually like to go with 0.05. So we're going to plug that in there. And then back to the Yates continuity correction. Do we need Yates continuity correction? We do that when degree of freedom is equal to 1. Our degrees of freedom is equal to 2. So we know we do not need the Yates continuity correction. Let's go ahead and just for our helper cells here, let's go ahead and figure out what our chi-square critical value is. This is the value that we're going to need to be higher than if we want to say that there are indeed differences with the machine's outputs now as it was before, to help us figure out, are we rejecting the null hypothesis or not? So I'm just going to go ahead up here and pull out a couple shapes so it's easier for us to look at the chi-square critical value table that I've copied into this Excel sheet. And we said our alpha is 0.05, so I'm just going to do a little coloring over that column. Get rid of the shape, bring in some red color. It's nice and easy to see. And I'm going to give it a little bit of a heavier weight so it's more visible for you. So this is the column we're going to find our values in. I'm just going to copy and paste that shape. And we said we are working with 2 degrees of freedom. So I'm going to just move that over the row. 2 degrees of freedom. And then look at where it intersects to find my chi-square critical value. And it's intersecting at 5.991. 5.991 is our chi-square critical value. Now that we have this base information, let's go ahead and calculate the chi-square itself. So in this point, we're going to start up in the expecteds. Now the expecteds have to be represented in Excel, and when we're generally doing this by hand, as a count frequency. If you saw the previous walkthrough video in R, when you do the goodness of fit in R, it wants to know the proportions. What we're looking at here, we need the counts. Big difference between these. So in this case, I'm going to go ahead and click equal sign. Click on my 200. Doesn't matter if you did the 200 here or down below where it says n equals. And we're going to multiply it by the percentage of our historical record. So we knew that 80% are produced at excellent. We have a sample of 200. So we should expect to find 160 are produced of an excellent quality. Let's go ahead and repeat this at the good. So I'm going to equal sign, click on the 200, multiply by the 17%. And you could type in 17% if you want. I just like doing the cell reference. Click enter. And we should expect to find 34 of good quality. Do this another one, find out the frequency of the unexpected. Click on 200, multiply by 3%. And we would expect to find 6 of unacceptable quality. And now that we have our frequencies observed and our frequencies expected, let's go ahead and start calculating the rest of the chi-square. O minus C, I'm going to do an equal sign. Click on 157 for observed excellent, minus the 160 of expected excellent. Tells us we have a difference of -3. I'm going to click and drag down. It's just going to copy those cell formulas and references down the line. Since I don't have any of those cells locked in place, it's just going to move dynamically and be just fine. The next step, we're doing a square. So I'm going to start with an equal sign. Click on the previous column cell where we had the O minus E. So here I'm doing the -3 of the excellent. And I'm going to do a shift 6 to get my up caret 2 to square it. And hit enter. So -3 squared is 9. I'm going to click and drag down. We now have 8 squared is 64, -5 squared is 25. Let's go into column F, row 3, and here's where we're going to take the observed minus expected squared value. It's going to go into the numerator, and then the denominator, we are going to divide it by the frequency expected. So I'm just going to click equals, click on the cell adjacent where we have our numerator value, divide by, and I'm going to click back on C3, which is our frequency expected for excellent. And so our contribution into the chi-square for excellent is 0.05625, and it keeps going. And I'm going to go ahead and click and drag that down to find out the expected contribution into the chi-square for the other values. And now we have those. From here, I'm going to jump down to B21, where I have a little spot to write in the chi-square statistic. In order to get that, we're going to start with an equal sign. We are going to sum, and we are going to add up all of those little contribution values we have up in F3 through 6. Close my parentheses. I'm sorry, F3 through 5. Close my parentheses, and it's going to tell us our chi-square statistic is 6.1 and additional values. So now we need to know, are we statistically significant? Well, to know that, we have to have a chi-square statistic that is larger than our chi-square critical value. Is 6.1 larger than 5.991? Yes, it is. So we would be statistically significant. We will reject the null hypothesis and say that, yes, indeed, the machine, after it's undergone some work, is producing at different levels of quality than it was before. At least one of those 3 levels of quality is different. The other two could still be the same. Since these are proportions, they will actually be different from each other since they sum up to 100%. Now, just if I wanted to be a little bit lazy or I had numbers and I couldn't quite figure out was my chi-square statistic larger than my critical value, I'm just going to do some lazy Excelness. Click equal sign, click on my chi-square statistic, greater than symbol, click on the critical value. If it says true, I'm statistically significant. And I also have an option where I can get the p-value of this. We get an alpha of 0.05, and I'm just going to confirm what I already know through my chi-square statistic and my critical value. So I'm going to do an equal sign, CHI. You will get a drop down depending on your version of Excel. You may see some different options in there. And I'm going to go down to where it says CHISQ.dist.rt. I'll hit tab and it will pop that in, or you can continue to type it as you go. Excel is going to give you a little pop-up here, and it says, these are the items I need in this function, where X is the chi-square statistic. So I'm just going to click on the cell reference B21 that has my chi-square statistic, comma, the degrees of freedom. I'm going to go click up on B19, which has the 2. I could have also typed in the number 2, close my parenthesis, and here it will give me a p-value of 0.047 and values. So we have 0.047. Is that less than 0.05? Yes, it is. If you were to round it, it would be 0.5. And we would say if we are at or under our alpha of 0.05, we are statistically significant. So yes, we're kind of skating the line here. We're on the edge, but we are still statistically significant at our given level of alpha, confirming what we had using the chi-square statistic and the chi-square critical value. Note the chi-square statistic and the critical value are very close to each other as well, which is what we're also seeing with that value and that alpha. So this is going to conclude the walkthrough of the chi-square goodness of fit in Excel. At the bottom of this, I have two separate tabs, one that says blank, one that says solution. So you can always click on the solution as well. This file is going to be uploaded in Elms for you, and you can compare these back and forth. I'll see you on the next video.